Okay, second part of the discussion, the potential function of a vector function. Now, at its base definition, a potential function is defined in this equation here, where the vector function equals the gradient of the potential function. Now, for this to be true, the vector function f must be conservative. And what that means is that if this is our vector function, where f and g represent some equations, respective equations, for a 2 vector function, the partial derivative of the f portion with respect to y must equal the partial derivative of g with respect to x. So that is, you need it to be conservative for it to work. Now, an example, don't know if it's conservative, just put this together very quickly, can be seen here. So the vector function f equals 3x and 3y. Now, what this really is saying is that the partial derivative of x here and the partial derivative of y, that's what it's based off of. So to solve for the potential function, we have to use the integral. So the integral with respect to x for the first portion yields this, and this is and the integral with the section portion yields this. Now, that, when combined together, equals the potential function. Now, this potential function has taken what was in a 2-vector, or could have been a 3-vector vector function, and has simplified it and reduced its complexity to a 1-component scalar function. And that's the power of the potential function. And an example is like an electromagnetism. It can be used, again, to reduce a complex 3-component vector field function to a 1-component scalar function. And that's its power. All right.